The last concept for today, because on Thursday we have to introduce a second way to do correlations for numbers that are not interval or ratio. I'm going to hold off that. I'm not going to do that all in one day. That's too much. But the last concept today is someone might ask, well, I've got my correlation. It is 0.60, which would be positive and fairly strong, but not perfect. It'll spread out like this, but we can definitely tell it's going upward. That'll probably be around a 0.6. Remember when I said that the correlation coefficient and finding this line tells you how much better your guessing would be? If someone said, well, if you know the x variable, how much better are you predicting y? How much less error are you making? Another way of saying how much less error is how much of the variability in the y variable is accounted for by knowing x. How much change in weight is due to change in height rather than other things? How much change in college success is due to or accounted for by knowing SAT scores? How much change in income can be accounted for by extra education? How much?
Isn't that what the slope is for?
No, the slope tells you just the direction and the general strength of the relationship, but it doesn't tell you the percent of the variation. And if we want to know the percent of the variation, we have to do one extra calculation. Okay? And R is a measure of the variability generally, but there's a thing called the fancy name the chapter talks about it. The fancy name is the coefficient of determination. It just says how much change in y, percent-wise of the variability, is accounted for by knowing x. The simple way to do that is, notice how we change it to a capital R so that we know we're talking about the coefficient of determination. But really it's just Pearson R squared. So R squared equals the big R, which is coefficient of determination. So even though it's a fancy concept, calculating it is easy. But what is important to look at then is the relationship between when you square a number that is less than 1. The further away from 1 you get, the more difference squaring makes. So if my correlation was 0.9, my coefficient of determination would be 0.81. 9 squared, 81. But if my correlation was 0.8, well, that doesn't seem very much lower. What would R squared be? 0.64. Oh, that's dropped actually pretty significantly. 0.7 correlation. So oftentimes when we do analyses or experiments, we'll say, ooh, I found a really strong significant correlation. My significant correlation was 0.4 between two variables. That's pretty good. That is definitely statistically significant. But someone else would ask, well, okay, but how much better are you guessing by knowing that? What percent of the variability in y do you now account for? Well, what would this be? Well, that's great. That's probably better than nothing. I've accounted for 16% of the variation, but guess what? That still means 84% of the variation, I have no idea what's causing it. When they were doing the identical twins rooted apart study at Minnesota years ago, They would bring in twins that were separated before 2 years of age on average, raised in completely different homes, had no contact with each other until an average age of more than 23. Some of them had never met each other again before they actually showed up at the experiment, and they were often 50, 60 years of age. The big question at the time was, is there any influence of genetics on intelligence? Early in psychology, they said, well, yeah, duh, absolutely, of course. Middle years of psychology, duh, absolutely not. And so, starting in the 80s, they were going back and saying, well, maybe there is. But the only way to really do that experiment was to see if there is a relationship between identical twins reared apart. So genetics are constant. The only thing that differs is environment. Once you get enough sets of twins, you can correlate the scores between the two of them. And what behaviorists suggested was you might find a 0.1 correlation, maybe less, but if they've been raised in different environments, it should have no impact whatsoever. What they actually found was, in the variation of studies across place, across time, different countries, whatever, anywhere between around 0.7 and almost 0.9. So somewhere between 50 and 80% of the variation in intelligence among these adults was due to their genetic makeup. If it was as low as 50%, that still leaves 50% of the variability not due to genetics, but no study found it less than that. And it just revolutionized the field of psychology. You guys don't realize that when I started, in Gen Psych, there'd be 3 or 4 chapters just dedicated toward learning theory. We wanted classical conditioning, operant conditioning, everything was behaviorism still. Now, learning theory is one of the smallest chapters in the book, and I was looking, if we were going to offer a learning theories course, try to find a full learning theories text among the major college publishers. 4 publishers, I found 1 book. Almost nobody's even teaching it anymore as a standalone type of discipline. It's amazing how things have changed. So again, you couldn't do an experiment where you picked twins, randomly separated, put them in random homes. You couldn't forcibly do that experiment, but if you could find natural experiments where that had occurred, it was still correlation, but it was powerful correlation. It gave you a pretty good insight into what you might be finding. So, let's look at one problem quick. I'll probably give you 2, maybe 3 problems for Tuesday. They all follow the same pattern. Okay. Say a graduate student is in developmental psychology, believes there may be a relationship between birth weight and subsequent IQ. She randomly samples 7 psych majors at her university, gives them an IQ test, figures out their weight at birth of the 7 from the hospitals. They had to get permission, of course. And here's the data. So in other words, we've got 7 sets of scores. So if I have just 7 sets of scores, for all that hairy experiment, how long would it take you to just if you have your calculator out, just dump them in quick. We've got about 4 minutes left.
In this case, the IQ would be the X normally, right?
Well, they're trying to predict IQ from birth weight. They think this influences that, so you make this the X variable, and you're trying to see if it predicts the Y variable. Now, what I might ask you to do on some quizzes, or definitely on the exam, that big hairy formula or whatever, I might ask you to put the numbers in the right place, show your work, but not calculate it, just use the final answer. But just show me that you know how to find, if you needed to, sigma xy, sigma x, sigma y, put it in the right place. but your calculator's already giving you the final answer, so you should be able to do a problem like this. Whereas again, back in my day when I was young, you know, doing this on a slide rule, this is a 20-minute to a half hour to an hour problem. On your calculator, this should be about a minute and a half problem.
Am I doing a two variation again?
Yes, this is definitely two variables, and you have to enter them in. This is how you know it's a two variable stat problem. There will be an extra column, pair number, student number, ID number, subject number. Some way that says these scores have got to be kept together in this order. You mix them up, you've got nothing. Where do you get?
For which one?
R.
0.7.
Okay, 0.78. That's a pretty strong correlation. Okay. And so a lot of these problems will have this form. Construct a scatter plot, okay. What's the value of Pearson R? Okay. Now this one says eliminate certain scores. I'm probably not gonna have you do something like that. And then it'll ask coefficient of determination or percent of variability in the number of days absence accounted for by knowing the number of cigarettes smoked. All the problems will take this form. So it looks hairy, it's very confusing as you read through it, but read the chapter. But solving the problems themselves